Okay, okay, all right. Okay, here we go. Well, this is the end of a conference, so I think it's, and we've accomplished a lot. I think we have been able to have a lot of very, very interesting presentations, very well done, a lot of very interesting dialogue between the scientists and also the public. And the purpose was to try to understand, I guess, really also, what our bulwarks are. But I was thinking mainly what we needed to accomplish in the conference is to find out where we really needed to be focusing our research. And the bulwarks are a place where we can be confident and safe and say, okay, we know these things for certain, but we need to be moving out into the frontier. And we were finding out where the frontiers are in the various different presentations, and it's been very, very good. This afternoon, we're going to begin with Dr. John Baumgartner and the second part of his talk, and I think you'll find it absolutely fascinating in terms of what he's going to be going over. And then after that, I will be attempting, I will emphasize that, I will be attempting to read Dr. Andrew Snelling's geology, his 4 lists. And there are some words on those lists I don't understand. So I can't possibly explain the entire sentence or paragraph if I can't even understand the words. So, but Dr. Baumgartner is here. So I will fall back on his expertise, and if he doesn't understand the words, then we'll just make something up. No, we won't do that. We can't do that. But let's open in a word of prayer, and then I'll turn it over to Dr. Baumgartner. Father, we thank you again for the conference we've had, and I ask, Lord, that you will bless John as he speaks, and we pray, Lord, that you receive the honor and the glory. May we be a blessing to you, to each other. Help us, Lord, to be clear, and I pray, Lord, you'll help those who are listening to understand, so that we may be understand more about your greatness. We want to study it, as it says in Psalm 111:2. These things are studied for their delights. We study your word for the delight of that, in being able to understand it, and then to obey it, and then to teach it. And we also pray, Lord, you will help us as we strive to understand your world, and then to teach that. May we be able to be persuasive in what we have come to understand of the way we should be looking at your world through understanding of your word. So again, may you receive all the honor and glory through this time. We pray in Christ's name. Amen.
Thank you, Steve. It's been a delight for me to be participating in the conference, and to me it's a greatly needed type of exercise that we're engaging in, trying to understand just where we are in our efforts to defend the early chapters of Genesis. Last time I primarily focused on the issue of deep time radioisotope dating, and also trying to understand the tectonic aspects of the flood. And today I'm going to mainly be talking about how the fossil-bearing sediment record came to be. And I would say until recently, this question, these issues have been more in the category number 4 of a frontier, where we had very little insight as to how the flood could have produced this thick column of layered sediments in just a few months' time, or even a few weeks' time. quite a challenging issue. And I would say it continues to be a major challenge. But I'm excited to share some of the discoveries, insights I've been making since I've decided to engage seriously in trying to get some answers about 9 years ago. I gave a presentation in 2013 at the ICC, and another one this last time in 2018. And most of what I'm sharing today is taken from my presentation at the 2018 ICC on this work. So an effective defense of the Genesis flood just cries out for a reasonable explanation for how, in the span of only a few months' time, this huge volume of fossil-bearing sediment came to blanket the continents in the orderly patterns we observe today. This record is especially well displayed in the southwestern U.S., in the national parks, and simply driving around in states like Utah, Nevada, Arizona, New Mexico, Colorado, where there's not so much vegetation covering the rocks, and we can see in the national parks and in highway cuts, road cuts, in many cases spectacular exposures of these flat-lying sediments. And so I yesterday alluded to several features, but I'll just say that this record is remarkable in many ways. One is the lateral extent of these layers, some of them covering many hundreds of thousands of square miles. And in many cases, these layers are not restricted to just North America, but are global in extent. And the sequence is global in extent. And some other aspects of this record is that the boundaries between the layers typically are flat planar surfaces that are not cut by erosional channels. And one would think if there'd been a lot of time elapse between the deposition of layers, that the processes we see operating at the Earth's surface today would have operated and cut gullies, channels, and created significant topography. But we do not see that as a general rule. We see very little of that in this record. And in addition, many of these layers internally display evidence of very rapid water processes. Large dunes, for example, that require rapidly moving water to have generated this structure. So the record itself, and in addition to all of that, we have this thick sediment sequence on top of the normally high-standing continents. How was that accomplished? And in addition, most of this record contains fossils of marine organisms. So all of these aspects seem to be crying out for some kind of process radically different from what we see going on happening on the Earth today. In other words, in the case of this record, the present is not a good guide to the past, isn't the key to the past, as Lyell and most geologists today understand the record. And I would say that, again, just to reemphasize what I just said, if you look at the surface today, there's a marked contrast with what we see today with what we see in the record. This little figure is an attempt to describe, to represent the typical drainage pattern, a dendritic pattern on the continents today. The higher topography is dissected by erosional channels. Sedimentation is generally localized to stream and river valleys. Again, in glaring contrast with the style we see dominating the fossil-bearing rock record. So if we're trying, as creation geologists, creation scientists, if we're trying to account for this record in terms of the Genesis flood, and that seems to be demanded by the biblical text, that the fossils we see are the result of a cataclysm, a water cataclysm that happened only a few thousand years ago, then we have some real challenges as far as trying to account for this record in terms of the flood. Some of these challenges include just the staggering volume of rock that we have to explain. It corresponds to an average thickness of about 2,000 meters or 6,000 feet on average over all the continental surface on the Earth. A second issue is I already mentioned, is the location of this sediment. It's on top of the continents whose surface generally lies above sea level, even though, as I said, the organisms, for the most part in this record, are marine organisms. Third is the vast horizontal extent of individual sediment layers, with little or no erosional channeling between successive layers. Let's see what it. Okay, so I've already illustrated those things here in that picture. A fourth issue is the presence of beds separated by bedding planes on the scale of centimeters to meters as a common characteristic of sedimentary rocks. This is what I'm talking about. As you look at road cuts and other features, this is typically the type of sedimentary rock formation you'll find. These laterally uniform beds separated by very well-defined bedding planes. So how does that characteristic of the record come about? The fifth thing is that the manner in which these fossil-bearing sediment layers are organized into 6 massive packages known as megasequences, separated one from another by global scale erosional unconformities. And that is illustrated in this figure, this slide. Larry Sloss was a geologist, worked in the oil industry, and published this idea, this concept, back in the 1960s, and where their survey of the sedimentary record in North America seemed to reveal this sort of pattern. Now let me try to explain what this figure represents. You'll know across the top one, there's an arrow pointing to the continent center on the left of that region that's either yellow or green, and on the right, continent margin. So if you think of this representing each half of the continent with the center marked where it is and the margin on the right, and then look at these sediment packages, which are represented in green, you see there are 6 of them named there, starting with the Sauk, Tippecanoe, Kaskaskia, Absaroka, Zuni, and Tejas. And you see the jagged lines that bound each of these regions of sediment. Each one is referred to as a megasequence each one containing many individual formations, many individual layers. But each of these megasequences is bounded on top and bottom by a continent-wide erosional boundary, unconformity. And you also see that these megasequences are more or less continuous and complete on the edges, on the continent margins, but largely very little of them is found in the continent interior, in the middle of the continent. So what is behind, this was a mystery and continues to be somewhat of a mystery for secular geologists, but it's also not obvious from a biblical creation standpoint how this pattern might have arisen, especially in this short time frame. So that's an issue, a challenge to explain. And then finally, we have regions of the continental surface known as continental shields, including what's known as the Canadian Shield, Baltic, Siberian, African, Indian, Australian, and Antarctic shields, which are large areas of exposed Precambrian, silicate, crystalline, igneous, and high-grade metamorphic rocks that have experienced significant erosion, are nearly flat, and have negligible, if any, sediment cover. And there are places that it appears that there's been up to 1 kilometer of rock eroded away from in many of these areas. So it appears that there's been very intense erosion occur, eroding away of crystalline rock that's was above what's the surface that we find today. So that's another challenge. It might appear that it's very likely that this erosion took place during the flood. So we're talking about some pretty intense erosion in these shield areas. And this is a map showing where the major shields are. There's the Canadian Shield there in Canada, in Greenland. There's the Brazilian Shield, or that's divided into two shields there, in South America. And then in Africa, much of the African continent is more or less barren of sediment today. Then you've got the Baltic Shield, or Scandinavian Shield in Scandinavia. You've got the Siberian Shield in Asia, although it does have sediment cover on it now. You've got the Indian Shield. Most of India has very little sediment. You've got a shield in Antarctica, and then the northwestern half of Australia is basically a shield. So and then these other areas shown in green here commonly represent thick layers of sediment. So I want to now describe my own attempts to address these issues. Now, it's been fairly recently. I gave a talk in 2013, so it's been roughly about 8 years ago. I've been working on this for about 8 years, and I decided it was time. This is such a major unaddressed issue that I decided, well, I'm just going to give some of my attention to it. Try to do something about this issue that we've, for the most part, been most creationists have just considered it too difficult to address in a serious way. My approach, since I have had quite a bit of training in this, was to try to develop a numerical model, a numerical simulation tool for investigating the large-scale erosion, transport, and sedimentation processes that operated during the flood. And I just want to give an overview of what this model entails. It is based upon a computer program that I developed in the early 1990s that solves what are called the shallow water equations on the surface of a rotating sphere. Now, I did this as part of a research grant, research effort there at Los Alamos National Laboratory. The intent was to try to come up with improved ways to model the ocean and atmosphere on the Earth, on a spherical surface, on the surface of the Earth, mainly for using in ocean modeling and also atmospheric modeling. And so I used the grid that I developed with my Terra code, and worked with another very gifted numerical person in my group to solve the shallow water equations. And that what that means, the shallow water approximation, as it's called, treats the water, or if it's the atmosphere, the air on the surface of the Earth, as a single vertical layer but with variable bottom height. And the advantage of that is that you convert what generally would be a 3D problem to simply a 2D problem on the surface of a sphere. Okay, so anyway, I back in those days spent a moderate amount of effort working on that, to develop that, perfect it so that it gave very accurate results. And just as an aside, the German Weather Service heard me give a presentation on this work back, I think it was 1994, and invited me over to Germany because they were working using were exploring very similar methods, and they wanted to compare with my specific algorithms with theirs, and because mine was had higher order accuracy, it was pretty clear to them. It was clear to them very quickly that mine was superior to their approach, and so they ended up building a whole entire global weather forecast model based on these numerical methods, and it's still used in Germany and at least 20 other countries, that global model. So it's these techniques are well tested. That's my main point here. Further, this numerical model for studying the flood assumes that the dominant means for sediment transport was by turbulent, rapidly flowing water over the continents. And the so-called theory for open channel turbulent flow was I applied to treat those processes of suspension, transport, and deposition of sediment. So there are a set of equations called the equations for open channel flow that involve a layer of turbulent water. The turbulence allows sediment particles to be retained in suspension, and these equations allow you to model the transport, suspension and transport, and then the deposition of sediment in a flowing layer of water. Okay, and this is basically an engineering issue, and hydrological engineering. There are lots of practical applications of modeling floods, flow in river channels, in man-made canals and channels. And so those equations are well validated. And so that theory is mature. All right, then in terms of erosion, I assume cavitation, which involves, in this turbulent flow, creation of small bubbles where there are pockets of low pressure. If the pressure drops below the vapor pressure of water, you can have these bubbles form, and then when that parcel of fluid moves into a region of higher pressure, those bubbles can collapse, implode, and they do so very violently and can produce pressure spikes in the pressure range that's able to destroy a crystal, a mineral crystal. Exceeds the shear modulus of silicate minerals. So it's an effective way for destroying the surface of a rock and converting those crystals into fine fragments, fine particles, and very effective erosion process. The secret is having a high enough velocity, having the water turbulent enough where that process kicks in. But in the framework of what I'm modeling, those conditions would be satisfied most of the time during the flood, where you had this column of rapidly moving water over the continent surface. And then finally, as far as what mechanism could possibly drive the water in this manner, create this turbulent layer over the continents, I found that repetitive large tsunamis generated by rapid plate tectonics provide the forcing needed to sustain the required water velocities. Okay, now just a quick little few slides on showing the power of tsunamis. I won't read all this, but in 2011, off the east coast of Japan, there was a 9.1 earthquake, and it was the most powerful earthquake ever recorded in Japan, and it produced a large tsunami. It was that tsunami that destroyed the nuclear power station there on the east coast, and the tsunami reached heights inland as it ran up inward from the coast, 133 feet above sea level, and it traveled as far inland as 6 miles. And I have a few photos of that. Here's the tsunami is beginning to top the seawall, which was intended to block tsunamis, but it wasn't constructed to deal with a tsunami of this size. So here it's coming over the seawall and beginning to sweep everything in its path, sweep it away. Here's a photo a little later, and basically there's hardly any building that was able to withstand. There were a few buildings, reinforced concrete buildings, that the structure itself withstood it, but generally speaking, everything else associated with the building was destroyed. So it led to massive destruction. This is what it looked like after the tsunami came through. Another shot. There was almost 20,000 people killed in this event, and some 130,000 buildings completely destroyed. So you see that these tsunamis have a great destructive power. And so how is a tsunami produced today? Well, it generally occurs in a subduction zone where an ocean plate is plunging into the earth, and this sequence of panels shows basically how that occurs when you have a ocean plate subducting into the mantle. The overriding plate tends to lock against that downgoing plate. So the downgoing plate is moving down continuously, and the overlying plate, when it's locked, is being continually dragged down, as you see in image B here. And then in image C up at the top, let me get my laser pointer. Hold on just a second. So this overriding plate locks as this plate continues to go down. This overriding plate is deformed. You have elastic energy stored in this region here. That deformation continues until the point where this locking is taking place. The irregularities on that surface just cannot stand that much stress, and they break, and there's a sudden slip, and this region rebounds elastically to its original shape. And when that happens, all this extra water that came to reside in this area is then pushed upward, and you have a large wave generated, which moves in both directions. And even though this wave can cause great destruction at great distances, generally the most intense destruction is the wave that is launched inland, as you see here. So that's just in a nutshell how a tsunami is generated. And again, this occurs in the subduction zones at these deep ocean trenches, where you have a slab of ocean plate or ocean lithosphere that's plunging into the mantle below beneath an overriding plate. Often the overriding plate is a continental plate that has a layer of continental crust that gives the continents the buoyancy and is responsible for them to be typically about 2.5 miles above the bottom of the oceans that rise up that high. It's because of this layer of lower density buoyant rock. In any case, it's when this region where the locking occurs, when that breaks and the plates slip, it generates earthquakes. And so that's where that it happens in today's world. And let me just, so what I'm, okay, so my model involves having regions where that subduction is taking place to generate tsunamis, okay? So at the 2013 ICC, I presented this model. All of this, what I just described, was in that 2013 paper, described in detail, all the aspects, all the equations. However, up until recently, I had not included the continent motions. I just had in that earlier study, I just had a static continent. Most of the studies were done with just a single circular continent. And but since that time, more recently, the work I've done, it added a displacement history for the various continental blocks, spanning in terms of geologic nomenclature, the Paleozoic, Mesozoic, and Cenozoic eras. In other words, the portion of the geological record formed during the flood. Now, so these next slides, I want to just give you an idea of what that, including that continent motion, what that entails. Okay? Now, there are a number of people that have worked on, most secular people for the most part, worked on reconstructing the continent history from in the Earth's past. And this is a map from that produced by Ron Blakey. He's a emeritus professor of geology at Northern Arizona University. And this is his reconstruction for what's called the Neoproterozoic. In the secular time scale, it's 560 million years ago. In terms of the flood, it would be just after the onset of the flood. So the pre-flood configuration, this is his reconstruction would correspond to just after the onset of the flood, and you see a continent distribution much different from what we have today. Basically, if you were to view this reconstruction from the South Pole, you'd find all the continents basically centered with the center near the South Pole of the Earth. And so I'm gonna suggest that this is probably the best idea we have for what the pre-flood world was like, where it was located on the Earth relative to the Earth's spin axis. This has not been acknowledged or talked about very much in creation circles, even though I've known about it for decades. I just haven't said much about it. But anyway, we're okay, and so we have. I'm going to show you that when you rotate this configuration, it's almost identical to Pangea. It's not in many ways it's very similar to Pangea. We'll get to that in a moment. So let me comment on what you just saw. Those nearly impossible to discern in this projection. The Earth looked at from today's coordinates, looking at it, looking along the equator. The remainder of Pannotia, and by the way, that supercontinent, pre-flood supercontinent, is referred to by many people, and that's the term I use, as Pannotia. It includes Gondwana, which is a well-known term, which was composed of modern South America, Africa, Madagascar, India, Australia, and Antarctica. That part of Pannotia persists intact through the Paleozoic to become part of Pangea. So there was no breakup of that large part of Pannotia during the Paleozoic time, and it became part of Pangea. The remainder of Pangea also includes the blocks that later became modern China and other portions of modern Asia. I'll talk about that in a moment. Okay, so how do these people reconstruct the continent history like that? Well, it's based on the alignment of magnetic minerals in rocks that crystallized at that early point in Earth history. Such paleomagnetic determinations have been undertaken by hundreds of investigators since the late 1940s. So in other words, it's based on what's called paleomagnetism. All right, now I don't have time here to give the details, but it's possible to rotate Pangea, the Pannotia supercontinent, by 110 degrees northward along today's prime meridian, or zero longitude meridian. That's which runs up through Africa, through Greenwich, England, such that Africa and Pannotia lies on top of Africa and Pangea. I'll show that in a moment. When that is done, it becomes dramatically simpler to compare Pannotia with Pangea. One discovers that apart from the terrains that form Asia today, the two supercontinents are remarkably similar. And that should not be surprising given that the entirety of Gondwana did not change between the two supercontinent configurations, and that the blocks Laurentia, Baltica, and Siberia changed very little. So let's look at that. So this was the image. The one on the left is what I just showed, and the reconstruction of Pangea that I actually use in my computer model is shown on the right. And so you get from the configuration on the left to the configuration on the right simply by rotating the supercontinent clockwise by 110 degrees along the what's called the prime meridian, or zero longitude meridian. This line that goes up through Africa today. right here. You just simply, along an axis that goes through longitude 90 degrees east, you perform a 110-degree rotation, and you simply move this distribution on the left, and it becomes something like the distribution you see on the right. This is I would say, a fairly significant discovery. I don't know anyone else that has pointed that out, but it's very useful in trying to understand what happened during the flood. So that's what I say in this slide here. It's possible to rotate Pannotia by 110 degrees northward along today's prime meridian, such as African Pannotia. Okay. All right. I'm sorry, I went the wrong direction. All right. So a vital issue when we consider that type of rotation, and when we consider that, let me back up and use the figures. When we another thing I want to emphasize here is that explaining if going from Pannotia to Pangaea during the flood, what that is saying, we've got to go somehow from this configuration, a configuration like this at the beginning of the flood, to a configuration like this sometime during the middle of the flood. That has to take place quickly, just in a few weeks' time. So how in the world are we going to do that? How are we as creation scientists going to be able to explain how that could happen? Okay, and so then the issue of what's known as polar wander comes into play. A vital issue is whether the large changes in paleomagnetic latitude are to be interpreted as what's called apparent polar wander or as true polar wander. Interpreting these changes as apparent polar wander implies that the magnetic and rotational poles have remained largely fixed and where they are today, and the continents have moved vast distances. That would be apparent polar wander. It's not real polar wander. It's the continents that have moved relative to the spin axis of the Earth. Or the other alternative is what's called true polar wander, and if that's the case, the amount of required continent motion is reduced dramatically. In other words, the Earth's surface, in the case of true polar wander, it means the Earth's surface has moved relative to the spin axis of the Earth. So and so as I'm saying here, it's much easier to account for this change in the latitude of these land masses if you have true polar wander. And true polar wander does happen. And I don't have time I can't go and explain that, but it is a reality. The brief time span of the flood accentuates this contrast between the consequences of these two possibilities. And I again say it's difficult to conceive of a mechanism by which the huge Gondwanan continent might move around the Earth by more than a quarter of the Earth's circumference in just a few weeks' time. You just can't, catastrophic plate tectonics is hard for most people to imagine, but this would even be, it would even compound that issue, having that kind of rapid continent motion if it was just apparent polar wander. Okay, I'm sorry, I keep going the wrong way. All right, so from these considerations, the choice I make is to assume that 110 degrees of true polar wander of the Earth's spin axis occurred during the flood, most of it during the early stages of the flood. I found that appropriate to choose the axis, the plane in which the polar wander occurred, as I've already described, to be today's 0-degree longitude or prime meridian. So when you do this, the Africa in Pannotia then coincides with the Africa in Pangaea. And then in my code, to account for the Coriolis effect, it's very simple. I simply alter the orientation of the spin axis to reflect that true polar wander. And but I have in terms of my computational grid, it's in the frame of this rotated continent. So when I do that, all the motion of the continental blocks corresponds to actual plate motion, if that true polar wander is a correct assumption. All right. Now let's look at the task of incorporating the actual continent motion in the numerical model. So basically, I have 11. I divide the continent, that supercontinent, into 11 separate blocks, and then I separate this time interval between the onset of the flood and the end of the flood into 10 separate time intervals, equal amount of time, and then so I've got 110 numbers I need to deal with. Actually, I'm sorry. So it's possible to represent the motion of one of these blocks over the surface of the sphere in terms of what's called a rotation pole. It's a vector with 3 components, x, y, z component, that specifies the rate of displacement of that block over the surface. Okay, so I just by hand, very tediously, came up with these, corresponds to 330 numbers, 110 of these rotation vectors, one for each continent block and each time interval. Okay, so then I'm going to show you what that displacement history looks like. When viewing this rotated supercontinent. So I'm going to just step you through these 10 of these time intervals. This is the initial configuration, and I've added some topography. So color corresponds to the initial topography, I'm assuming, and then I'm only showing the vectors indicate which way the continent is assumed to move during the interval, each of these continents. So this block remains stationary, and these 3 blocks pull away: Laurentia, Baltica, and Siberia. And so this is the initial condition. This is after 10 days after the onset of the cataclysm. This is now 20 days when these blocks have moved apart. And then at this point, the blocks amazingly start to come back together it's going to form Pangaea. So first of all, Baltica slams back into North America, producing the Appalachian Mountains. And then Siberia then slams back into these 2 blocks to form some other mountains, the Ural Mountains. And then these 3 blocks then move back to basically their original positions, forming the Atlas Mountains and the Southern Appalachian Mountains. So all of that is well documented in the geological record. The opening of a proto-Atlantic, which this would be the proto-Atlantic here, and so there's plenty of evidence that actually took place, and in our framework, it happens during the flood. So these blocks slam back into this Gondwana region. Now, I forgot to mention, I've got, it turns out that much of Eastern Asia apparently started out as part of, located down here on this part of the original supercontinent. So I have, rather than add the complexity of separating out a North China block and a South China block, I've left them together. They don't exactly, aren't exactly moving together in the secular model, but for our purposes, that's including them as a single block is fine. And basically, about this point in geologic time, this block breaks away, starts migrating, and eventually slams into this northern continent up here. And so, so that's shown here. This is at 90 days. This block slams into this northern continent, and then later this block starts. Gondwana starts to break apart, and this northern supercontinent breaks away from Gondwana along here. So you have the Atlas Mountains left on Africa. You have the Southern Appalachians here on North America. I'm sorry, the Atlas Mountains right here. Okay. All right. So then later in this sequence, you have a further breakup of Gondwana, and the northern continent breaking away, Laurasia, or North American Greenland, breaking away from Europe. And so this is the way that continent motion is managed, is implemented in this numerical model that I'm describing. So now I'm going to show an illustrative case with the water motion driven by large amplitude tsunamis, and these tsunamis are generated in subduction zones that suddenly unlocked and generate the tsunamis. Okay, and just some details. I assume these subduction zones are in that big ocean surrounding the supercontinent. I don't worry very much about exactly where the subduction zones are. I'm mainly concerned with them generating tsunamis. I'm taking for granted that the location doesn't matter that much as far as the effect of the tsunamis on the continents. Okay, and I'm using the same kind of plate velocities that I get from my Terra code on the order of 2 meters per second in generating the tsunamis. I'm not going to go into time, but spend a lot of time on this. But basically, I have a tsunami generated every 6 minutes somewhere on the Earth. I have 16 different segments that slip. So each section that subducts and locks and then slips is about 1,500 miles long, which is actually longer than I expect it really was. And it slips about once an hour, and I've got 16 of them. Each one, there's one every 6 minutes. So that's equal to 240 per day, or 36,000 over a time span of 150 days. So here we have, I'm assuming 36,000 mega tsunamis during the course of the flood. So that's the kind of violent, and these tsunamis have an amplitude of more than 1,000 meters typically. That's 3,000 feet high. So you've got a wave, tsunami wave, invading the continent that's roughly 3,000 feet, 4,000 feet high. So it seems to require that kind of intensity to generate, as I'll show, generate the amount of sediment that we have on the continents and distribute it inland to blanket the continents the way we see the present day sediment record doing. Now, in just some more details about the continent and the ocean, the oceanic region is taken to have a uniform depth 4,000 meters below the mean sea level. That's roughly the depth of the modern day oceans, average depth. And in the case of the continent, it varies smoothly from 200 meters below sea level at its edge up to a maximum of 1,000 meters above mean sea level in the continent interior. Initially, the water is assumed to be at rest with its surface at sea level, and continent surface is assumed everywhere to consist of crystalline bedrock, and the Earth is assumed to be spinning at its current rate of rotation. Okay, so I'm going to show you snapshots in time when I let this calculation run and let this mechanism, these tsunamis be created, let them slam into the continent and erode the continent edge, transport the sediment particles inland, deposit them when the tsunami comes in, slows down. The turbulence decreases. When the water velocity decreases, it drops its sediment. The wave moves out, and another tsunami comes in. That's repeated some 36,000 times during this calculation. So this is a snapshot in time at 20 days. Let me try to explain what these colors represent. So I'm representing with color here the height of either the water surface or the land surface if the land surface if there's no water on it. So in this case, this is just for the most part the original topography. There's no water here. In the ocean area, though, you see these high waves that are larger. It's being clipped at 1,000 meters height. Some of these are like 1,500 meters high. So these waves are coming and impinging on the continent as the continent these blocks are moving, as I showed in that previous sequence. This is a view from the North Pole. So you can see, okay. So next pair of slides are showing the depth of the water that, in this case, that's above the land. And here I'm clipping the values at 30 meters, or about 90 feet. So we have water running, coming up onto the continental surface, but not reaching all the way into the interior at this point. Okay. Next slide is the cumulative bedrock erosion. And so, as it might not be surprising that the most intense erosion is occurring where these tsunamis that are traveling at 200 meters per second in the deep ocean, that's about the speed of a jetliner, abruptly encounter the edge of this continent that is rising 4,000 meters or about 12,000 feet up from the ocean floor. When that tsunami slams into the edge of the continent, you might imagine a lot of turbulence, a lot of erosion takes place along that boundary. And indeed, that's what's going on here all the way around. So here the maximum red is being clipped at 150 meters. In some areas there's twice that amount. So, but to try to represent it here, I clip it at 150 meters. So essentially, almost all the continental margins are being heavily eroded by these tsunamis. These two pictures show the amount of suspended sediment, and here the limit is 50 meters, or 150 feet of solid equivalent is being suspended in the turbulent water column. So we're talking about pretty heavy-duty turbulence to be able to keep in suspension 150 feet of solid equivalent sediment in the water column. So we're moving a lot of sediment onto the continent here. But it's variable. It's not all, it varies. There's quite a bit of variation there in that slide at that point. But this is the cumulative, net accumulative sediment deposition at 20 days. So you can see that here the maximum value is 350 meters. So we're moving a considerable amount of sediment onto the continent here, and this is just at 20 days. Okay, so we begin by having the flood affect these margins of the continent, and bringing and depositing a considerable amount of sediment over these areas. Now, as far as trying to understand the fossil record, we see that the areas being affected at the beginning stage are the coastal areas. The higher topography inland areas, there's nothing happening there. So it might not be surprising that we're primarily burying in this record, in this early record, burying shallow marine animals for the most part. But then starting as this water moves inward, we're eventually starting to get coal layers of fern type plants and animals, plants and animals that would have been living in the very the lowest elevation land areas. Okay, a snapshot at 50 days. This is after 50 days. And this is the height of either the continent surface or the water surface. And by now the continental surface is being modified considerably. You've got quite a bit of sedimentation that's already occurred. You have these mountains that have formed, and so on. Plus, there's quite a bit of dynamics, up and down dynamics in the ocean itself. There's this large anticyclonic gyre, which is like a high pressure area where the water level has risen high. So there's going to be, it appears that there's a lot of sloshing and dynamics in the ocean itself. This is the water depth over land. You see the water is reaching further inland. This is a snapshot, so there's a lot of time variation in the water depth as these tsunamis are high at one point in time and low and not as high in other times. It's these high areas where the water's coming in, depositing the sediment. Again, this is a picture of the cumulative bedrock erosion. The pattern is very similar. We saw it 20 days, but here the cutoff is at 300 meters. So it's continuing to erode very strongly. And this is the net cumulative sediment deposition. Again, we see it along the coastlines, but now we see sediment deposited further and further inland. Snapshot at 80 days. Similar kind of thing. We have this block that broke away from the southern region right here, almost docking with this northern continent. We see consistently higher topography on the continental surface due to increasing sediment deposition. Let's see, did I get this? Okay, this is the water depth over land. I must have got the orders swapped here, but anyway, that's the water depth. Okay, have I already gone to 80 days? Okay, 80 days, yeah, it's 80 days. I went backwards instead of forwards. Sediment deposition, okay. Now we jump to 110 days, and now we see, I've increased the scale up to 1,500 meters as a maximum, but we're getting high, a lot of sediment deposition over almost all the continent now. We still have these tsunamis. Since I've changed the scale, they don't look as prominent, but you got some regions where the waves are greater than 1,500 meters in height. This is the cumulative erosion. Now we have a region where two coastlines have slammed together, and so all that erosion is now concentrated in that zone, even though there's no ocean in between. But this is the cumulative deposition that's mostly filled in with sediment here. Got a lot of sediment deposited in that region where the bedrock level was low. And so, okay, now the snapshot at 140 days. We have a lot of sediment deposited almost everywhere over the continents. The cumulative bedrock erosion and the cumulative sediment deposition. By cumulative, I forgot to mention that I'm allowing the sediment to be eroded away, put back into solution, and carried somewhere else. So this what's shown here is the net, what's left after the deposition and periodic erosion of these regions with sediment. Okay, now a little later I'm going to talk about how this distribution of sediment compares with the distribution of sediment on the continents today, and how there is an amazing correlation. Let me just review these challenges I showed earlier, explaining the volume, the location, the vast horizontal extent, the presence of beds separated by bedding planes, the megasequences, and the continental shields. So how well does this model at this point account for these things, like we saw? Well, I say first, the huge volume of sediment is being explained pretty well. This particular case I ran, I have approximately 2/3 at the end of 140 days. I have about 2/3 of the sediment we presently have on the continental surface deposited on the eroded, transported, and deposited on the continent surface. And it's deposited on top of the continents. This is a mechanism that enables us to account for why the deposition is on top of the continents. The tsunamis are able to do that. Okay. And then another thing which I've not mentioned up to now, it provides insight into the current directions recorded in the sediment deposits. And the details show that just as there are ebb and flow phases of a tide on a beach, the tsunamis display similar back and forth flow. In a tide, the ebb is the outgoing phase when the tide drains away from the shore. The flow is the incoming phase when the water rises again. In the case of tsunamis, the incoming phase has higher speed, is highly turbulent, keeps the sediment in suspension, and there's little or no deposition. By contrast, in the outgoing phase, the water speed is lower, the flow is less turbulent, the deposition typically is appreciable. In terms of the flow direction recorded in the deposited sediment implied by this model, the flow direction recorded in the deposited sediment is generally in the direction toward the coastline when the tsunami is receding. Okay, so that's as far as the current direction recorded in the rocks. If it's being deposited by these tsunamis, the current direction should be when the tsunami is moving out, is ebbing, when the flow is ebbing, moving toward the coast. Now, it turns out that work done by Art Chadwick, which I read his list yesterday. He's I would say the world expert on this issue of paleocurrent directions. In the case of this Laurentian supercontinent or block, the current direction in the model when most sediment deposition occurs is toward the west-southwest. It is noteworthy that the paleocurrent directions observed in the Paleozoic portion of the sediment record in the southwest United States are also predominant from west-southwest. This is in the direction of the west-southwest, according to Chadwick and Brand et al. 2015. So I'm matching. I'm able for the first time to account for the current directions that we actually find in the sediment record. Here's a quote from Art Chadwick's paper. During the Paleozoic, clear and persistent continent-wide trends are normative. Sediments move generally from east and northeast to west and southwest across the North American continent. This trend persists through the Paleozoic, includes all sediment types and depositional environments. So that's encouraging that this model is able to account for at least the Paleozoic paleocurrent directions. Okay, another encouraging insight is, and this is a prominent feature that has been ignored for the most part until now by flood geologists, and that is the thousands of individual beds separating by bedding planes in typical vertical sequences. How that can be explained? Well, it's the vast number of tsunamis that catastrophic plate tectonics generates that appears to be able to explain this. These tens of thousands of tsunamis. If I allowed the width of each subduction segment to be 750 kilometers instead of 1,500 kilometers, I'd get twice as many tsunamis. I think that's more reasonable. So we're talking about 70,000 tsunamis during the flood. And they diffract off a high topography, they diffract off one another. So you're producing multiplied pulses of rapidly moving water, able to generate this fine structure of beds and bedding planes in the record. I'm sorry I'm running over a little bit, but I'll try to wind up here shortly. Okay. All right, the final big insight has to do with the correlation in the global sediment pattern. All right, so I didn't really appreciate this when I gave the talk in 2013 at the ICC. I really hadn't had time to look at the data that well. But afterward, I realized that this pattern that I showed a moment ago matches this pattern of where the sediment is and where the shields are amazingly well. Let's start with the shield areas. Let's look at Africa. There's, most of Africa has very little sediment on it. There's this big thick deposit across North Africa and Saudi Arabia. Saudi Arabia, by the way, is right here in this model. So this correlates with this pretty well. We find the eastern part of South America not to have much sediment, whereas the western part, and this is the tectonic belt. So we're mainly focused on this part, and so that is works reasonably well. We see this part of North America there's this big shield area here in this part of North America, and sediment over to the west of that. And similarly for Australia, Western Australia has no sediment. India has very little sediment. And I'm not sure about Antarctica, how well it matches there. But anyway, I'm very encouraged that this model is able to reproduce the core at a coarse scale the general pattern of sedimentation. And so I'll have to briefly talk about this. In this model, I didn't assume any variation in the global sea level, but current work that I'm doing, I've currently put in the ability of the code to allow the global sea level to rise and fall 6 times during the flood. and at each rise, the height of the water is higher than the previous maximum. So the water is successively rising with each megasequence. The global sea level is increasing to the very end, and then you have a big runoff at the end. What is responsible for this variation in global sea level? Well, it has to do with the cooling of the ocean, of this newly produced ocean floor. And I allow God to intervene and cool the ocean floor enough for the next phase of subduction, but as the flood unfolds. But then toward the end of the flood, the majority of this new ocean floor is warm, and because that hot ocean floor displaces volume of the ocean, that global sea level rises, and then God at the end intervenes and causes all this newly formed ocean floor to cool, and you have this massive runoff of water off the continents, the stripping away of sediment, producing the landscapes we see today in places like Utah, Arizona, New Mexico. So anyway, this is an attempt to describe this. I have some additional things that I plan to put into the code. So in conclusion, this seems to be working well enough that I seem to be able to explain a lot of features of the flood, and seem to be able to move where the modeling of the sediment record is in this 4 categories that Steve has given us from the conference. Move from category 4 more to, I would say into category 3. Able to explain some things, but still many things yet need explanation. So I've just sort of scratched the surface. We've had more than a century and a half of secular geology, thousands of secular geologists working on understanding, documenting the geology at the Earth's surface. We only have a handful of creation geologists. So I believe, and so the secular geologists have documented lots of aspects of the rock record, but interpreted in terms of their uniformitarian worldview. So I believe, there's lots of work if we're going to explain things as well as they have attempted to explain things. So there's lots of work, lots of details that need to be fleshed out. But I believe this is providing some, starting to close the gap a little bit, giving creationists some framework now to start interpreting a lot of the details in a more confident and hopefully more correct manner. So I think I'm going to close it here at that.
Okay. All right.
So.
Thank you very much, Dr. Baumgartner. Mike? Okay, Gene?
Hello? Okay. In a recent Acts and Facts publication from ICR, Tim Clary was saying that Mount Ararat is a part of a ridge. I've heard various people say Mount Ararat, that the one that's called Mount Ararat today is a post-flood volcanic feature. But he was saying that this ridge of I guess is it sediment, is possibly older than that. And I was wondering, could one of these episodes that you were talking about have produced this ridge, do you think? And Would that help us with where the ark could have landed?
Okay, the issue of where's Noah's Ark. Some of you are aware that I succumbed to the temptation to be, one of those that was searching for the Ark back in the 1980s. Made 8 trips to Turkey to investigate this site south of Mount Ararat that was in, on Cretaceous age rock, and not, Holocene rock, not rock that was formed in the last 10,000 years like Mount Ararat. So it had a chance of being around when Noah got off the ark, this other site. So anyway, I've been involved in that type of issue for a long time. I personally do not think that ridge west of Mount Ararat is a candidate. There's that part of Turkey, actually the site where I was right at the suture zone of where subducted plate had plunged into the earth, and it was that event that produced all the magma and volcanism that led to the formation of Mount Ararat. And in that type of tectonic environment, I do not think that is an area where Noah's Ark where Noah would have landed, or I just don't think it's a good candidate. My own idea of where about the only place that I know of that's a good candidate is the site in far southeastern Turkey, a place that is documented in early Christian literature, identified as the site of the landing place of Noah's Ark. Many early Christian writers attested to that. And there's an inscription by, I think it's Sargon II, who made an expedition there, and or was it Sargon? Who was the, no, it was Sennacherib. It was Sennacherib. He came back and reportedly had a piece of wood that he had brought back, and it was in his temple there where he was murdered later. So there's an inscription on the cliff right there near this location by Sennacherib, and so I think there's several lines of evidence that the landing place of the ark was there. At elevation, it's right near the Tigris River, on the north side of the Tigris, right there, at elevation of about 6,000 feet. So that site is the site I would say is the best candidate that I know of. Unfortunately, it's an area, highly contested area right there where the radical Kurds have been, where it's been under martial law, Turkish martial law for most of the last 50 years, 30, 40 years. And so it's not easy. Right now it's impossible to get there to do any research. But anyway, I do not think that Tim is correct in what he claimed.
I just wanted to add to that the text does not say that the ark landed on Mount Ararat. It says in the mountains of Ararat. So we're looking for a region. We know that there was a people called the Urartian region, and that's probably where it is. However, in my own opinion, my own humble opinion, I don't think we'll ever find the ark, because I think they would have cannibalized it in order for firewood and to build houses and so forth. So I think it's gone. But as I said, it's in the region. It's in the mountains of Ararat. So it's in the mountainous region of the area or R2, which is around Lake Ermia and Lake Van. So that's the area. And there were expeditions by various different Assyrian kings up there to subdue rebellions. And I think one of them, I'm not sure which one it was now, might have been Esarhaddon, who died on an expedition up to try to quell the rebellions. Every time there was a change of king, there would be rebellions. Thinking that maybe we can now be independent again, but the Assyrian kings would come in and subdue them again, very harshly. So that was one comment. The other comment was about the Sloss mega sequences. There may be evidence in the text itself for something like this, because there are these successive the description of the water coming in, and it says that the water was the Mavul was on the earth for 40 days. Then the water multiplied and lifted up the ark. Okay, so that's the first thing. The water multiplied, and then the ark rose off the earth. Then it says the water became powerful. That's a second step. Okay, the water became powerful. Then it became very numerous over the earth, so much so that the ark now is traveling upon the surface of the water. It's not even talking about the surface of the earth anymore. And then it says, then the water, as for the water, it became then very, very powerful. So here we have another stage in the description. So that might, I don't know if there might be more. That might correspond maybe to those mega sequences. Just a thought. Yes. Anybody else have a comment?
The other thing is, if you look at that Hurricane Dorian, I sent you an email about it a little bit, and it got me thinking, because that was, as I understand, the first hurricane that stood still there around Nassau for 24 hours. Up until now, we've always seen them. They'll move slowly, but they're moving. And while it was sitting there, it expanded in aerial extent, and it got more powerful. And then I started looking about these Pineapple Express, atmospheric rivers. And the ones now that come out of the Hawaiian Islands, again, there's lots of hot spots there around the Hawaiian Islands, the water. And as you have seamounts, geos everywhere there in the North Pacific. So that water gets really hot, as this flood as Steve was saying, as it builds up in intensity. And these Pineapple Expresses now, what we observed, they're several hundred miles across. They call them atmospheric rivers. And they literally carry 7 to 15 times the water flow that you have at the mouth of the Mississippi River today. So I think water, maybe even in this preliminary phase where the ocean waters, this magma is starting to break open, Pangeas open up, what's happening as that water inflows from around the supercomet? It's flashing the steam, right? I mean, as you pointed out before. So we've got water, storms, hurricanes, the Carrie Emanuel hypercanes, which Larry Vardaman is, I think, pretty well duplicated. So, and then particularly in the runoff, those storms would be continuing to put a lot of water on the surface of the earth. And so now what we see is, the after effects of the reworking of those first 6 layers, right?
Yeah.
And so I think really now, based on what the people can see just driving around town, we need to, also put some emphasis after day 150, when, the mountains are beginning to rise up, because that's what, we're seeing a lot of today. And the Whopper sand, that Tim Clary identified. I think that's just nothing but awesome. How do you account for this? How did it get there? And then I think the computational fluid dynamics, if we could do some of that on the runoff and see if we could duplicate, the sheet flow, then the channelized flow, the start of the Ohio River Basin, because you can drive in these basins today, miles across, right? Huge amounts of flow going through there at one time.
Yeah. Well, I said, what I shared just now is just a very initial foray into this realm of trying to understand the geological record. But I believe we need to get the big picture right first, and then be aggressive in filling in the details.
So, did you want to ask a question first?
I was going to make, yeah.
Go ahead.
So secular geologists, how do they explain the water up over the continents? Is it ocean level rising, or what kind of force could push whole continents down into the mantle?
They basically explain the mega sequences by oscillations in the global sea level, but
do they have any mechanism for why the sea level would rise this
they
much?
basically attribute it to variation in the speed of seafloor spreading. That when the seafloor spreading is fast, you have more hot ocean floor around and the sea level rises. When the spreading rate is small, the average temperature of the seafloor is colder and the ocean basins are deeper and the global sea level is lower.
Have they put numbers on that? I mean,
No,
does that
they
have-
don't. They don't. It's more of a hand-waving kind of explanation.
Oh, okay.
So this explaining these laterally extensive layers, they simply, in my opinion, they seek to cover their eyes and their ears. They try to ignore it. They try to put it out of their consciousness. They have no explanation for it. Willfully ignorant, yes. And I might just say that the cross-section, I've had a cross-sectional map I got from my first visit at the Grand Canyon. I've had that on my wall ever since I became a creationist, just to remind me of how certain the explanation of that geological record is by the flood. That the flood is, flood is a certainty, and so I if ever I was started to be a little overwhelmed by all the secular claims, all I needed to do is glance at that map and be persuaded, no, the Bible is absolutely true. There was this kind of global cataclysm, and in Steve's framework, that's a bulwark I can stand on and be unmovable.
What about Steve Austin's idea of a laminar flow, something that's beyond, when you go beyond the turbulent flow, you end up in this different state where the water is actually sliding. It's like a slurry.
Right.
It can carry a huge amount of sediment long distances at very rapid speeds. Is that part of your?
I didn't dwell on it, but that was one bullet point in my last or next to the last slide about future improvements. I want to put basically a slurry, a layer of concentrated sediment as my bottom layer. Actually, on the continent, I do divide that turbulent water column into multiple sublayers, and I want that thin bottommost layer now to be largely sediment. that gets that is able to behave dynamically like Steve has been talking about. And but even without it, even without that feature, my model nevertheless deposits stuff not that dissimilar from what he's describing. You know, he's basing his ideas on these flume experiments that have been conducted. So, you know, geologists, hydrologists have been able to simulate things in a laboratory. Many of these done at this big lab at the University of Minnesota, where Henry Marsh worked for a while, and so I would say Steve's his ideas have been influenced by those experiments, but what I'm describing is a realm that those labs have never, probably they've never even thought about attempting to model. You're talking about a turbulent layer that's the layer itself is moving at these high speeds. They're at best modeling the very bottom portion of it, and they do not have traction at the top like my model has. And in my view, all Steve had to work with was gravity as a driving mechanism. And I concluded years ago that gravity could never produce the sediment record that we have. And that Steve's ideas were just too, I don't know what the right word is, provincial. He's too narrow, he didn't grasp the big picture. His mechanism could never account for this overall sediment record.
How thick is the sediment?
Well, the average thickness, as I said, is 6,000 feet, and there's a lot of shield area. So in some cases, it's 20,000. Some cases, 30,000 feet thick.
Wow, it's a lot of sediment.
Where I grew up in West Texas, there was. We were not that far from the Permian Basin, and we were sort of on the fringes of the Permian Basin, and there's some wells, oil wells there, 10,000 feet deep. So I don't know what the full depth of the sediment column was there under the Panhandle of West Texas, but probably 15,000 feet there. In much of mid-continent North America, there is those sorts of thicknesses.
That's amazing. Any other?
There's a river on the eastern part of North America, the New River. It starts in North Carolina, and then it crosses these ridges of the Appalachian Mountains. There's a bridge, a New River Gorge Bridge, where they have a holiday once a year where people can bungee cord off the bridge. Okay, and so it starts in North Carolina, but it joins some other rivers and empties into the Ohio drainage, Ohio to the Mississippi and on out that way. But it cuts through these ridges. So is there any feature of your modeling that would successfully explain how a river could have a channel that cuts through these high ridges of the Appalachian Mountains?
Well, I'm not. This model doesn't include the tectonic dynamics that accompanied the flood, but there's at the end of the flood, especially at the end of the flood, the dynamical forces that had operated during the flood, this catastrophic plate tectonics, the rapid motions in the mantle below, these sinking plates stirred the mantle, produced lots of motion in the mantle, flowing rock, that altered those flows deformed the surface. So one thing I don't have in the model I just showed was the up and down, what's called dynamic topography, that was produced by the flow in the mantle. So So there was that going on that's not in my model, but probably even more dramatic was what happened when all this rapid motion, this rapid tectonic motion shut down, and then this what's called isostasy. It's basically Archimedes' principle applied to rocks. When that kicked in, and all these regions where the crust had been thickened, where this continental crust, the buoyant continental crust had been increased in thickness, all those regions then bobbed up like a rock or a piece of wood that had been pushed down in the water. All these buoyant regions rebounded, came up to their equilibrium levels, and basically punched up all the high mountain ranges in the world, the Andes, the Rockies, the Alps, the Himalayas, and elsewhere. So there's a lot of that going on. A lot of the mid-continent U.S., the Great Plains, all the regions where you find all these fossils in Kansas, this earlier Great American Seaway, all of that region uplifted by at least between 3,000 and 4,000 feet. The plains earlier probably just after the flood was still below sea level, and all the high plains have uplifted, probably most of it after the flood. So there's been a lot of vertical tectonic adjustments that occurred during the runoff, the latest stages of the flood, and then after the flood. So most geologists are ignorant, oblivious to all of this dynamics, and most creation geologists are unaware of these adjustments that took place. I published a short article, impact article in Acts and Facts, entitled something like "The Recent Uplifts of the Mountains," and showing that all these mountains, all the high mountains, most of their uplift to their present elevations took place, at least, if not after the flood, the final runoff stages of the flood, when these driving forces of catastrophic plate tectonics went away, and you started having this isostatic adjustment. And so that's something that secular geologists, I pointed out in that paper, absolutely have no explanation for. It falsifies their framework. The uplift history of today's mountains being so late. If their model is true, that adjustment should accompany the forces that produced the thickening, but it didn't. There was the tectonics responsible for the thickening. Instead of being spread over tens of millions of years, in the flood model happened, during the year of the flood, and then when those forces went away, there was rather quick adjustment and dramatic adjustment. So this is an area that there's a big difference in the predictions of the models, and our model is the one that gets it correct. And you have a sudden uplift of the mountains, and in their framework, it's similarly just almost as sudden, having it being primarily the Pliocene and Pleistocene, several thousand feet of uplift. So, in answer to your question, I'm guessing that it might involve the uplift history after, at the final stages of the flood or after the flood, and that there was a river able to stay ahead of that uplift and cut through that uplifted topography at the end of the flood, where the rainfall rates were high, the erosion rates were still high, and that river was able to keep up it started, originally it was draining to the north, and as the uplift occurred, it continued. It was able to continue its earlier course and erode down and keep track of the uplift that was occurring. And so now these regions are high, and the river, is dissecting high topography, and I suspect it has to do with this uplift history at the end of the flood.
Eugene's got me curious now. So were those ridges that it cuts through, are those tectonic features, or are they water carved features?
I've recently moved to Virginia, and as I'm trying to understand how to travel from one place to the next, I'm realizing it's not easy to travel east-west in this part of the country because of all these mountain ridges that run north-south, or roughly north-south through Virginia, West Virginia, and so on. And so those ridges are primarily produced by erosion. Well, first there was earlier folding of sediments, folding, and the fold axis corresponds to the direction of the ridges today, and then the erosion, much of it after the flood, has taken away the less resistant regions, and the more resistant regions are the ridges today. So that large scale pattern is a result of the erosion, much of it probably during the flood, and then some of it after the flood. And so the larger scale topography is a result of that erosion of earlier folded sediments. And then what I'm talking about is finer detail on top of that, that was associated with the some of the uplift afterward.
This place he was talking about, New River Gorge, the Park Service, you go there, they have a model. Did you see that, of that whole area of the mountains there? A three-dimensional model. Yeah, it is awesome. It is fantastic. And you can see these channels being cut every which way, okay, until they finally sort it out and they start going down the Ohio River, and some went, the New River Gorge, I think, when it goes the other way, becomes the Potomac River before it goes out into the ocean. But now you've got these Appalachians coming up, you've got the Rockies coming up, so everything east of that continental divide is being pushed this way. The west of the Appalachians, it's running down these river valleys, and it's all running south. So the deepest wells, I'm really scratching my memory here, but an oil and gas journal, they would always publish the deepest wells and that. And they were down there in eastern Oklahoma. In fact, there was a deep one. This was a gas well in Arkansas, just across the border into Arkansas, some of the deepest wells. Well, that's where all this water laden with sediment is headed, right in that direction, to just keep piling it up. So now the question is, in Beyond is Genesis History, they had a clip in there showing computational fluid dynamics, that when you get to these high velocities, because these fine bedding planes like that, you see no evidence of erosion whatsoever. And what they were saying in there, and it makes a lot of sense, you had hydroplaning going on. You get to such a high velocity, particularly, I don't know exactly when these layers are going down, that they just shoot out, i.e. to form that Whopper sand, which is 200 miles offshore New Orleans. So I'd like to comment on that, what you know about that modeling that they did there in the hydroplaning. And then the other, forgot the, can't think of the other question now. But, yeah, that, and also in Flora State Park down there in Mississippi, you've got all these petrified logs, and they tend, I think, to align with the flow streams. I think we can see a lot based on the work Tim Clary's doing now, as to how this all settled out after day 150. Oh, I know. When the main thing for me with the tsunamis is the creation of the sediment through cavitation. In other words, how do you account for all this massive, massive amounts of this really fine material? You know, in a tranquil sea environment, you can't. So do we have any, what should I say, laboratory evidence? I know what Juliarad did with the Glen Canyon dam failure there, maybe plays into that can confirm what you're saying, that as these things come ashore, they're eroding sediment through the cavitation process like crazy.
Well, there has been a moderate amount of experimental study of cavitation, and the equation that's in the literature that I have in my code is a very simple equation, that the erosion rate from cavitation is some proportionality constant times the velocity minus a threshold velocity quantity raised to a power. And so there's three parameters. That's only three parameters in that equation. One is the proportionality constant. One is the threshold velocity, and that's pretty well, constrained, pretty well measured, somewhere between 10 or 12 meters per second up to perhaps 15 meters per second. In my model, I go with a more conservative number of 15 kilometers 15 meters per second, that cavitation doesn't really kick in until the water velocity reaches 15 kilometers per second. It's probably closer to 10, but I use 15. And then the crucial parameter, the one that really plays a big role, is the exponent. And that, it's been estimated between, I would say, 5 and 7, and I use 6 in my model. So that's a very simple kind of equation, and various experiments have. There's no reason to expect that it's really complicated. There might well be some pressure dependence in the model, sort of depending on the water depth. I could imagine that coming into play, but otherwise that model is pretty simple. And I. Yeah, that would come the way I fold that in, because I apply this both to sediment and to crystalline rock. It comes into the this proportionality constant on the front, but it may well affect these other parameters too. So yeah, but even with the crude, and I'm trying to be fairly conservative, model for cavitation, I don't have any trouble in producing enough sediment in my model.
I have two comments. I remember at a rate meeting, there was a naval officer there, and he was talking about that cavitation is so severe in the rudders and so forth in the ships. They have to just the ship moving through the water, and with the screw, that they have to watch out for cavitation and really damaging the rudder and the blades of the propeller and all of that. That was one thing I thought was amazing. And we're talking there about steel. The water is just eating up the steel just because of these bubbles popping and then, and releasing that force. Another thing is, again, back to the text in Genesis 7:24, it talks about, it says, and the water was powerful upon the earth for 150 days. It doesn't say the water was on the earth for 150, it says the water was powerful. So the first time it became powerful, remember, it wasn't immediate. First of all, it was multiplied and then became powerful. So I've been starting to do some computations about maybe when that power started to happen. And also I think we need to maybe be considering that the Mabul itself was only on the earth for 40 days. And so the profile of the flood is a very rapid rise and then going down for about 325 days. But still, it was powerful beyond that 40 days, whatever powerful means. And I assume powerful would mean cavitation and all that kind of, eroding, all that kind of stuff. So there's things happening that, for the first 40 days that don't happen after that. But then there's this phenomenon that's going on for 150 days from whenever that began. In our modeling, we need to be, I think, considering that. Anybody else have any questions? We need to, I think, move on to the next section. It's almost 3:30, and we do want to read Dr. Snelling's, or I want to read, or I've been told by Dr. Snelling to read his lists. So I think I will go up there with Dr. Baumgartner, and maybe with this mic as well, and we'll have two mics, and then we will he can make comments as I read Dr. Snelling's list. I think that's what we'll do. So if we could bring up the list,
Yeah, I'm working on it here.
Okay. Okay. I can actually bring the list. I could actually look at the list. I will. Oh yeah, all of these videos are on the website. Yeah, they will be there. So I think let me bring up my list here.
Box there to make it.
Oh, wait a minute. Yeah, but I have to be able to read it here. Oh, it's something else. Wait a minute. Okay. So I'll have this one, and we'll have the one up there as well.
Okay, where do you want I didn't see it on this. Do you want like one here, and then the other one too close?
Okay.
Like
Well, I thought I
that?
would just use one here, and then he has this one here.
Oh, okay. Like that?
Do you want this one?
Oh, you're gonna be at the
Okay,
podium?
well then you're gonna have this, I guess. Well, then do you want this? You have the other list, or can you just look at that?
I can.
Can you see it?
See that one?
Okay.
I'll take this one, I guess, if you're.
Okay. All right. So
Somehow I hit-
you can just move. Oh, it's okay. Oh, okay, close it. No, it's fine.
There it is right here, isn't it?
There it is. So you can just move it like that.
Okay.
All right, have a seat. All right. Can you all hear me? Good. All right. It's Bulwarks and Frontiers in Creation Research, contributed by Andrew A. Snelling and you can read his biography. It's on the SIX's webpage, SIX standing for the Center for Interdisciplinary Creation Studies. And he followed the 4 lists, and like everyone else, it seems like his Bulwarks list was very short. So what things you know for certain, I would call these things a bulwark, and creation research, we as researchers really don't need to spend any more time, effort, resources on these things. Andrew took my words and put those in red, and then his comments are in black. So this is his bulwark. The universe and everything in it, the earth, animals, and plants show abundant evidence that they were designed by the intelligent creator. And we all agree on that bulwark. So, is this, oh, this doesn't move like that. How do I move this? Oh, I see. Okay, down here. What do you know for the most part, but still have questions? These things are not totally nailed down yet, in contrast to one in which they are. The first one is, where is the pre-flood and / the flood boundary in the geological record? Now, what he's talking about here is, as we look at the rock, the layers in the rock record, where is the beginning of the flood? Somewhere at the bottom of those layers, where did the flood begin? Correct? I think that's what he's asking. Where is the pre-flood flood boundary in the geological record? And paleontology could contribute to this, understanding a lot of different things in order to understand the pre-flood flood boundary. Now, this is something that no one else has discussed yet. How long did the post-flood ice age last? Because there was an ice age, and there's an excellent description of how warm water, which was at the end of the flood, and caused so much condensation, so much rain, that in the cooler areas, it was precipitating snow faster than it could melt. And as a result, we have an ice age. And I think it was about 700 years from the time it started until it ended. But if you want a really excellent description of that, you go to the website isgenesishistory.com, and there is a interview there with Larry Vardaman. Or you can look at the Is Genesis History and look at the DVDs Beyond Is Genesis History, and the one on, I guess it's probably Rocks and Fossils, in which Dr. Vardaman talks about what caused the ice age. But there obviously are questions, otherwise Dr. Snelling would not have asked them. How long did the post-flood ice age last? Where does it begin and end in the post-flood biblical chronology? And there are some who think that the book of Job evidences an ice age. So these are questions that we definitely have. What things are we making a little progress on but have many more questions than answers? And what I did was I didn't add any words to his list, but where it impinged directly on the biblical record, I put it in blue. So what is the most accurate biblical chronology? That based on the Masoretic text or that based on the Septuagint? It is well known in biblical studies that the Septuagint text is different in several places. It is different in the 5 fixed dates for the flood. And we have the Masoretic text, that's the Hebrew text. We have the Septuagint, which is a Greek text. And we also have the Samaritan Pentateuch. We have the Vulgate. Those are the main witnesses to various different dates for the 5 fixed dates of the flood account. But also in the genealogies in chapters 5 and 11 of Genesis, the Masoretic text, the Septuagint, the Vulgate, and the Samaritan Pentateuch all should be consulted. And he's asking the question, what is the most accurate biblical chronology? Now, it's well known in Septuagint studies that the Septuagint is a harmonizing text. And that is the reason why in chapter 11, it adds the phrase at the end of each generation, and he died. It's absent from the Masoretic text. It's clearly the case that would be a much harder text. And the principle of textual criticism is which text could have arisen from the others, and then which is the more difficult text is probably the original text. So the Masoretic text, since it does not have Vayakum, and he died, is the much more difficult text. And so the Septuagint was adding probably to harmonize with Genesis 5. And so also there has different dates for the lives of the patriarchs that just preceded, the line that just preceded Abraham. So that's that question. You can jump in anytime you want, John. What is the chronology of the flood, including when the rains stopped and the fountains were closed, and when the waters peaked, as well as stages of the retreating waters and the drying out, all of which have implications for the geology, geophysics, and paleontology of the flood? All I can say for that is stay tuned for volume 2 of Grappling with the Chronology of the Genesis Flood. This is exactly what we're working on, the internal chronology of the flood. The first book was concentrating on the methodology that would be applied to the flood to determine the flood chronology. This is the issue of actually applying it. So some things that I know again is that the water the mechanisms that the Bible said were responsible for the water, that is the fountains and the rain, that stopped on day 40, on the 40th day. So but the waters remain powerful, and I don't know whether that means that the waters were at the same level, but they still remain powerful for 150 days. Now that they became powerful, according to my calculations, between about 9 and 16 days into the flood. Now that calculation is based upon, believe it or not, looking at the flight of the dove. Don't have time to go over that right now, some other time. But we are working on these issues. Also, I think it's important is that the double infinitive absolute in Genesis 8:3, describing the retreating water, is that the waters were retreating continually. Also, there are different words that are used for dryness. One word which is used for the fourth fixed date, and then another word which is used, that's the word charev, and the other one is the word yavesh, which is used at the end, the end of the flood, at the point in which the Lord told Noah to bring out the animals. So we're working on that, and but we certainly need to be working on it not just with me and my guys who are predominantly Hebraists, and with one geologist, Dr. Snelling, but with geology, geophysics, and paleontology. We all need to be working on this issue of the chronology of the flood, because our geological model of the flood should start with what does the biblical, what are the constraints put on any geological model by the biblical model. I think that's what we all would agree with that. So I think we all need to be working on it, and that's what I wanted to do. I wanted to have everybody involved with producing this work on the chronology of the flood. And maybe now we can do that. At what point in the fossil and rock record is the highest level of the floodwaters, and what date does that correspond to in the flood's biblical chronology? I think, okay, that's similar to the question further down, or I'm not sure. At what point in the fossil and rock record is the highest level of the floodwaters? Oh, okay. That's saying it's kind of like, when you have a flood and you see how far it went up on the wall or went up on went up on a pier, and you can see how far the water went up. Can we see what was the highest level of the flood water in the rock record? And so that is again a very interesting question, and I don't have any answer for that. If all flesh had died by day 150, as stated in the text. Now I put that in yellow because I think they all died by day 40, or shortly after that, and I try to support that. Then how much longer were the animals still carried dead in the floodwater before their carcasses were buried in flood sediments? And this is a question, I think, predominantly for Art Chadwick to answer, because his specialty is from when the animals died until their final burial, which is called taphonomy, correct? So that's the issue there.
Leonard Brand, it might be considered more of a specialist in that than Art Chadwick.
Oh, okay. Leonard Brand, okay. Where does the landing of the ark in the mountains of Ararat? As he said here, actually it's Urartu, not Uratu. On day 150 coincide in the geological record. And obviously this is the idea of where did the ark land? And it does say in the mountains of Ararat. And we want to know where that is. And as I said, we find this place, Ararat, we find this location mentioned frequently in the Assyrian sources because it is one of the areas, somewhat near Assyria that they always had to subjugate every time there was a change of government. Every time a new king came in, the people in the Urartians, they rebelled, and it's most likely the Kurds think that they are, and they probably are, descendants of the Urartians, and so and it appears in the archaeological record that the Urartu is the source of the chariot, and so that's also very interesting. That we know that there was a trade between Urartu and Egypt, and that's probably where they got their chariots. And also Solomon became the world chariot emporium. All the chariots were sold in Israel, and he was the center of it all. Was becoming fabulously wealthy in the chariot trade, and talking about. God said, don't multiply horses, and instead he multiplied horses and chariots to the point that he was the big chariot trader in the world. How do you explain this wisest man? That's another issue. That's another conference. Okay, now this is the one I know that John has in this question has some slides from Tim Clary. Where is the post-flood boundary in the geological record? You have them on here?
It's getting late. Let's just move ahead. I'll just say, this mic is not working for some reason. You know how to turn it on? It is working?
Yeah, it's working. Yeah, it's working.
Okay.
Yeah.
Tim has written a paper he plans to publish very soon on this issue of the post-flood boundary. He is, as many of you may know, he's been sort of the one who's picked up what used to be called the Column Project to try to have a good database for all the sediments in the world, based, including all the drill cores that the oil companies have made, and these huge databases. So he's picked that up and has carried it. He's done a good job for North America already. He's worked on South America, Africa, and he's most recently started Europe. And basically this paper that he hopes to publish soon has to do with the sediment record in the area around Turkey, but it also includes Eastern Europe and the Middle East. And what he's showing is that there is thick marine sediment formations through the Cenozoic, through at least the Miocene, all around Turkey. If the end of the flood was say at the what we used to call the KT boundary, more recently the KPG boundary, Paleogene boundary, that all this area where Babel is, where the mountains of Ararat are, would have been inundated with marine sediment after Noah got off the ark, which Tim considers just unthinkable. So he thinks, based on this marine sediment record, that the post-flood boundary has to be high, very near the end of what is called the Cenozoic. In other words, probably in the Pliocene, before the Pleistocene Ice Age occurred. So very late in the record, prior to the time of the Ice Age. And that is also my conclusion, that from geophysics evidences, from many lines of evidences, just the existence of these laterally extensive layers all over the world in the upper Cenozoic. I believe the flood was not over until the late Cenozoic. There's so much ocean floor that came into existence during the Cenozoic. At present seafloor spreading rates, you can have at most a kilometer of new seafloor in the last 4,000 years at present rates. So in order to get these, hundreds and thousands of kilometers of new seafloor, the mantle has to be dramatically weaker, orders of magnitude weaker than it is today to get that much seafloor spreading. That requires the weakening mechanism that I appeal to for catastrophic plate tectonics. So I'm saying catastrophic plate tectonics absolutely did not end at the KPG boundary. It continued through most of the Cenozoic. And also there are evidences for these tsunamis in the oceans, these geos, these flat top mountains, not only in the Pacific, but in all the oceans of the world. I believe especially in the time scale of the flood, you do not cut the top of these volcanic mountains off in a short period of time unless you have tsunamis active. And I would even appeal to the Waimea Canyon on the Isle of Kauai in Hawaii that is eroded out of solid basalt there on Kauai. That seems to require tsunamis to do, Kauai has a date, a Pliocene age. So it appears to be there were still tsunamis, which implies rapid plate tectonics there in the Pliocene. So to me, there's so many multiple geological indications that the flood did not end until the Pliocene, causes me to be pretty firm, pretty confident that that's where the flood post-flood boundary must be. And I'm saying that so we would have the runoff being the late Cenozoic, the latter part of the Cenozoic was when there's massive runoff. And that, again, if you look at the age of the Whopper sand, you look at all of this runoff erosion that filled the Mississippi Valley, it seems to me just to demand a late date as far as the record is concerned for the end of the flood.
John, also all the brown coal deposits that I've seen, so they're lower in rank than the subbituminous that we have out in the outer river. So be it in Kalimantan, Borneo, in Indonesia, Australia, the Yalorenstein. I don't know about the Hat Creek, but up in British Columbia, which is like 1,000
Yeah, Mississippi and Texas. Yeah,
Desert mine
yeah,
down there,
yeah.
where you have the bark and everything. So you're reworking and thrashing and shredding a lot of floating debris, conventional
That's
matter,
right.
to make these mountains of coal.
Right. For those, we just have one mic here just to repeat this comment by Ken Carlson about these brown coal deposits, many of them 1,000 feet thick, in the Cenozoic, some of them in the later Cenozoic, Miocene, seems to require flood conditions to transport, to gather and transport such huge volumes of tree material and produce these thick coal deposits. And there are many of them around, in many parts of the world, throughout the world. And that seems to be another powerful argument that the flood processes continued throughout most of the Cenozoic.
Okay. What's interesting about this question is there are those who on the other side, and I don't take either side. I just want to follow what the Scripture says and put the constraints on the geological model. And I think that as I said, that the difference between Gava and Mut and how they differ from Macha to wipe out the existence. And we should be looking at that in terms of what we find in the fossil record, and maybe that will help us answer this question. Anyway,
let me just comment for people that may not have listened to Todd Wood this morning, the evidence for the other side.
Okay.
And that is primarily, as far as I would say, it's largely has to do with the fossil record,
right,
the mammal record, and the distribution of mammals. And in his case, he mentioned 3 different types of evidence. One was the one was the evidence is that there was a sudden interchange of mammals between North and South America when the Isthmus of Panama was established in the Cenozoic. So I don't take that as something we can't understand and account for. What was his first one? I'm trying to remember.
he was talking about the mammals that were above the KT and those that were there's just very few below. I think he mentioned that, but he says they were not really, maybe not connected to the ones above.
Okay, yeah.
And he mentioned the names of the mammals that were found below the KT, but for the life of me, I couldn't. Well,
one of them was the monotremes.
There you go.
Okay. But he also, another one he mentioned, not in that when he was addressing the KT, well, in another context, he mentioned the marsupials in the fossil record are in Australia, where the modern marsupials are located. And so he was arguing that it's unlikely that the marsupials that were killed in the flood, that the marsupials on the ark would migrate back to where their ancestors were before the flood, which I agree. It seems a somewhat unusual, but I can imagine that happening. So again, I don't consider it something that trumps everything else, all these other evidences. Okay, let's move on.
Yes. Here and why, how and why, are the vertebrate fossils in the order they are in, with many marine and freshwater invertebrate fossils mixed in with them, but no mixtures of unrelated vertebrates in the same layers, such as cattle with dinosaurs? I think that is a question for paleontologists to answer. What he's saying is that there's mixtures with marine, the vertebrate fossils, the order they're in, with many marine and freshwater invertebrate fossils, but there's not a similar mixture with cattle and. I'm just messing it up. Let me move on. See, I knew this was going to happen. Okay, so can we identify the North American megasequences in every continent and convincingly correlate them. So the idea is these slots megasequences, do we find them on every continent, and can we say, okay, are the bottom one is the same bottom one that we find on North America, and so forth and so on. So if we can find those megasequences are even larger, they're very large on North American continent. Look at this Genesis history, the movie. But if we can find out that those things are go across over into Europe or beyond, or even global, that's a very strong evidence for those megasequences for a global flood. So I think that's what he's saying.
I think this question could be tighter, could be expressed in a little tighter way. We know that these fossils tend to appear globally, so the formations are global in extent. The crucial issue is whether or not these erosional unconformities that separate what we call the megasequences are global. Whether these bounding unconformities are global in extent. I think that's the real issue here that he's trying to get at.
And they're at the top of the sequences, right? The unconformity?
Yeah, they're at the top of the previous sequence.
And the bottom of the other one?
Yeah.
Okay. Okay, how many more individual rock units can be correlated across continents and between continents, such as has been done in part with the peat sandstone, red wall limestone, and the Cretaceous chalk beds? So what he's saying is there something like that the peat sandstone, let's say, over in Europe? Or is there red wall limestone over in Europe? And if there is red wall limestone, one of the indications of that would be a nautiloid kill right in the middle of the red wall bed. It would be an indication that that's a red wall.
Let me just say that, what's his first name? Auger, the book, the stratigraphical record, Derek Auger, claims the red wall is global. It certainly extends into Europe, and I think he mentions in the Middle East and Australia. The Tapete sandstone, Steve Austin claims, is easily observed in the Middle East, even in southern Israel. So at least, I think Derek Auger also claims these Cretaceous chalk beds are global.
Right, we see the cliffs of Dover. There's chalk along the French coast, along the German coast. I mean,
yes,
there seems to be a lot of it.
Has photographs. Auger documents that very well in his book.
Okay, and for the next question, we have Ken Carlson here. Can we develop a comprehensive model for coal bed formation during the flood that accounts for the different paleofloras in the northern hemisphere, Carboniferous coal beds, and the southern hemisphere, Permian coal beds, aka the floating forest biome, as well as the different paleofloras in the Mesozoic and Paleogene coal beds? If you can understand that question, you go to the head of the class. Okay, he's just saying, how do we explain the formation of the coal beds? And Kurt Wise has worked on this, and this is quite. I think the old models of coal formation that I learned in elementary school, okay, and oil formation, all these things are being reconsidered. And but if you want to know all about coal bed formation, you can talk to Ken Carlson, and as I said, Kurt Wise, and also Steve Austin. So and hopefully next year we can get those guys. We can get Steve Austin and Kurt Wise here. So.
Just a quick comment on that, based on Steve Austin's PhD dissertation. I think it was the Kentucky #9 scene in western Kentucky. 90% of that, and that's a bituminous coal, the high rainfall, was the bark, just the bark,
Mm-hmm.
lycopods.
Right, of lycopods.
Okay, what we are finding down in these low brown coal deposits
Let me ask you a question, since you're the coal expert. Anthracite coal. So I'm from Pennsylvania, where the anthracite coal, I think it's all been mined away, but you know, coal, the only kind of coal you can pick up and not get your hand dirty, you know, because it's like glass. Yeah. So where'd that come from?
Also in Pennsylvania, these, the anthracite coal seams tend to have significant dip to them. As you get to the top layers, they're very uniform, horizontal. China, they were mining up coal that was literally vertical in there. So what you have is basically like the Lawrence seam in Australia, 60% moisture, inherent moisture, okay, as opposed to surface moisture. And then they look like, consider a sponge with a lot of water in it. As you're loading this thing up, and we don't know how deep it was pre-runoff, you've got a lot of weight pushing on this stuff, just squeezing that water out. So there's no moisture, inherent moisture left in those coals. And I think that's a big contributor to the change in rain, is just compressing
Okay.
with all that weight, which is huge.
You want to add to that, John, or?
Yeah, I'm not an expert on that, but I would guess that it's a matter of more pressure on the
Okay.
pressure and temperature on the anthracite coal drove it to.
Uplifted because of the mountains, like the Appalachians moving up, then it takes that horizontal seam and it's pulling it up too.
Yeah, when you the fact that these layers tend to not be horizontal it implies they were in a tectonic belt, probably experienced higher pressures, higher temperatures.
Okay, thank you very much. How are dolomites, limestones, phosphorites, and evaporites, which are precipitates and salt deposits, sourced and deposited during the flood? So he wants to know how these specific minerals and rocks, these types of rocks and minerals, were deposited, because they are results of evaporation. So how are they sourced and deposited during the flood? These are various different questions. Okay, how much of the rock and fossil records of the flood were destroyed by the erosion of the retreating floodwaters? Well, I told you, I was looking there, and there's an anticline here. What do you mean? Because an anticline is a big bow like this, okay, of rock. A syncline is down like, you see, sin down, okay? Anticline is up, and I was seeing, you know, layers pointing up like this on one side, and about 10 miles away, layers like this, and in the middle, nothing. And they said, well, that's the anticline. What do you mean that's the anticline? Well, what happened was all that stuff in the middle was all cut away with the regression of the waters. So this is pertaining to this question. How much of the rock and fossil records of the flood were destroyed by the erosion of the retreating floodwaters? So, yes.
Well, I would say you look at the Grand Staircase in Utah, in Arizona, and you get some idea of how much sediment was stripped away. A good 10,000 feet of sediment is missing to the south that you find to the north. So in that region, you have on the order of 10,000 feet, or maybe even more, of sediment stripped away. You go to these national parks in Utah, Monument Valley, Arches, Bryce Canyon. Canyonlands.
Yeah.
And that terrain is a documentation of massive stripping away of sediment. And the landscape that remains is the what's left after this rapid, massive denuding of sediment has taken place.
I talked to Mike Ward once about this very thing, and he was saying that he'd done some calculations on these anticlines and the fact that a lot of that material is missing. Then he looks at the continental shelves around the continents, computes how much material we have there, kind of correlate.
Yes.
I
Yeah.
don't know, I've never seen it published anywhere, but
Well, Roy Holt published a paper in the late 1990s where he documented the massive amount of Pliocene sediments, Pliocene sediments, arguing that this has to represent the runoff, stripping away of the sediment that had been deposited earlier by the flood, by the transgressive phase of the flood. And this sediment that's on the continental shelves today represents material stripped away during the regression of the flood waters.
I would just say, if you want to see what the flood did, in terms of deposition of sediment and also of removal of sediment, just visit the national parks of Utah. And also the Grand Canyon, but particularly, you can see the sediments that were deposited by the Grand Canyon, and the Grand Canyon was not cut during the flood. It was something happened afterwards, but you can see the sediments there. But if you want to see, as I said, as John said, 10,000 feet from the bottom of, I guess, the Colorado Plateau all the way up to the Clarion Formation at Bryce Canyon, and even above. Cedar Breaks. I mean, this you can see it's absolutely spectacular. It's beautiful, but you can also see huge amounts of erosion. And the park their official explanation for this was mind-boggling. It was fog froze and broke off pieces of the rock, and took millions of years and eventually carved Bryce Canyon. But you need to go to Bryce Canyon and see it. It's it's 9,000 feet. It's amazing. And it's really clear skies and wonderful air. Okay, how do we fit the archaeological record with a post-flood geological record together in the post-flood biblical chronology? So how do we fit, there's a question I'm going to do with the Bible. How do we fit the archaeological record? Now, and I think archaeology needs to come into this. So we need to bring an archaeologist into this team that we're assembling, in a sense, with a post-flood geological record in the post-flood biblical chronology. So we have to look at the biblical chronology, look at the archaeological record, and look at the records of these ancient civilizations, of Sumer, of Akkad, of Egypt, of the Indus Valley, of the Hittites and their precursors. We need to look at this to understand. We need to put it all together. We cannot do it in isolation, and it takes experts in those things. I'm not an expert in archaeology, okay, and nobody is here. So unless I'm mistaken, how can we calibrate the post-flood? This is a question for John. How can we calibrate the post-flood radiocarbon inventory and carbon-14 ages with the post-flood biblical chronology to help realign the archaeological record with the biblical chronology? Go ahead.
I consider this a high priority for us. That this is there's a great urgency to get this done and come up with the answer to this. Basically, the rate project showed that that there is radiocarbon in every fossil that still has carbon in it, and at levels way above the detection levels of these instruments. But what we, in trying to understand it with the flood, we find that prior to the organisms that lived before the flood, preserved in the fossil record, had to be very low in radiocarbon, and then it appears that during the time after the flood, the radiocarbon level had to quickly get to modern levels, what was where did all that radiocarbon come from? It appears that you need a source other than the atmosphere to give you a source other than cosmic ray produced C14 in the upper atmosphere as is occurring today to get to those high levels soon after the flood? The answer that was implied in the chapter, in the rate chapter on C14, was that there was likely C14 produced in continental rocks by accelerated nuclear decay during the flood, and that C14 outgassed, got to the surface, got out of the rocks after the flood, and rapidly raised the C14 level to modern levels. So, but that's yet to be, that was more of a hypothesis, a conjecture, an implication of accelerated nuclear decay. It would be nice if we could go to these rocks, go to the rocks and look for still C14 still present in the rocks to validate that hypothesis, to confirm that hypothesis. So, but this is an issue. Another question I would raise has to do with the which chronology between the Masoretic text and the Septuagint text, which begetting ages are the correct ones? Is it are they the ones in the Septuagint or the ones in the Masoretic text? And this has become a point of debate. Henry Smith, and I forget the other guy he works with, they have recently been claiming that, giving arguments that it was the Masoretic text that was tampered with. One of the texts was tampered with deliberately. Was it the Septuagint that was deliberately changed those begetting ages, or was it the Masoretic text? And the time when that would have occurred would be the time after 70 AD, after 130 AD, when the Jews were finally dispersed, and there were just a handful of rabbis left in Jerusalem that had control of the text. And Henry Smith claims they had motivation. They were under great pressure to refute the claim that Jesus indeed was the Messiah. But the rabbinical history had claimed that the Messiah would come within the first, the first 6,000 years of the world, before the year 6,000 in their calendar. So let's see, no, maybe it was 4,000. No, yeah, 4,000. Anyway, he said they had a motivation to try to shorten the chronology, to help fight against this claim that Jesus was the prophesied Messiah, and that it's the Masoretic text that was tampered with. But for us, that makes a big difference, whether the flood was in 2350 BC or was in 3100 BC. If it was in 3100 BC, we have a lot more time to fit in all this archaeological history. For us, it's hard to fit in, have an ice age and all these Paleolithic peoples and all this history, to fit it in if the flood was as recent as 2350. So I say this is an important issue. It's one that it's definitely one that we need to be addressing and having people work on in an earnest way.
And also involved with this, as I said, is to consider the record of ancient peoples, like when were the earliest pyramids built, and the earliest pyramids are from the Third Dynasty, which is in 2600 BC. So these are some issues, and even earlier ziggurats built in Sumer. In any case, we need to move on. Where do Earth's impact craters fit in biblical Earth history? Which Danny's not here, especially those claimed to be pre-Cambrian, such as the Sudbury and the Vredefort. So
Sudbury in Canada, the
Vredefort.
Vredefort in South
Holland?
Africa.
Oh, in South Africa, okay. So
And-
these are
and-
impact craters that were Precambrian. Was down below, way down in the rock record.
So they would have had to occur during Creation Week.
Right, during Creation Week.
So that causes many creationist heartburn to imagine other bodies, big bodies, impacting the Earth during Creation Week.
Yes.
And I myself, I commented that I think that, the case that is true is probably solid, and I got almost kicked out of the ICC back in 2013.
Oh, wow.
Danny Faulkner went ballistic. So anyway, let me just leave it that this is an issue that deserves further attention.
Okay, and I think along with this is how much the Precambrian geological record is Creation Week and how much is pre-flood. He said per-flood, but he means pre-flood, and what sections of that record can be assigned to each of the creation days. I think that is very ambitious to be able to say that this section is for each creation day. But maybe it can be done. How much process do we allow for in the formation of the sequences of Precambrian rocks during the Creation Week versus Fiat creation, as is when most Precambrian sequences often display multiple cycles of erosion and sedimentation, volcanic eruptions and lavas, regional metamorphism and tectonics, and intrusions of granites, as well as the formation of many ore major deposits. So you need to understand that Dr. Snelling is an igneous and metamorphic geologist. Steve Austin is a sedimentary geologist. So when Dr. Snelling is saying these are things that we can see in the Precambrian rocks, these things which we would normally, erosion, sedimentation, volcanic eruptions, and these things happened before the flood, and which means something between creation, either during Creation Week or sometime between there and the beginning of the flood. So a lot of stuff was going on geologically even before the flood. And that's what he's looking at.
And so some of the best preserved examples of what he's talking about are in Western Australia. And they're of interest because there are ore deposits. And Andrew Snelling was trained in that realm of hard rock geology, exploration geology, looking for ore deposits. So his training has exposed him to these realities that he's describing here.
Gary, you have a question?
Yeah,
Loud.
I just went with Andrew Snelling on the first Grand Canyon trip back in 2006. We went to the Inner Canyon, and we looked at the Precambrian rocks there, the schist and the granite.
Mm-hmm.
And my thinking is, I just was wondering, isn't there sort of an assumption like Precambrian? So somebody says that Precambrian, they talk about creation rocks. Are we assuming that Precambrian has to be creation because of Genesis, the third day, or could it be post-fall? There could be some after the fall, some type of geological events, including in which would be these craters, because there would be a post-fall Precambrian rock event, but not necessarily during the Creation Week. Why do we have to assume that Precambrian means creation rock? I guess that's what I'm asking.
I guess it's because that's when there were very large geological processes when the waters are moving away in order for the dry land to appear. This sounds like a huge geological process.
He holds that those basement rocks are day 3 because you've got sedimentary rocks below the deep sandstone, which don't have any fossils in them.
Right.
And so he says that those rocks were day 3 creation rocks.
Well,
Grinding.
as far as let's separate this issue of where did these Precambrian sediments come from and when were they deposited from when did these igneous rocks and metamorphic rocks and metamorphic history, when did that happen? And in response to what your question, I would say that many of these metamorphic kinds of events imply catastrophism that would have been problematic for life after life was created. It's just some of these Precambrian events are so dramatic, so large scale, that it causes most of us that have looked at this problem to have to place it during day 3.
Okay, let's see. Okay.
Another key point along that line is if you look up, like on Google Scholar, for example, paleosalts, and you look up Cambrian, and then you look up Precambrian, the thickest ones are in the Precambrian, several meters thick. There was a paper by some professors at the University of Wisconsin and Tokyo, University in Japan, that found these very thick paleosalts. So where we're supposed to have all this plant growth and rapid development, you would expect to find good soils there. We have virtually none that we can really cement down as being rock solid evidence for paleosalt. But in the Precambrian, there's lots of them. So that's, and how can you have a lot of tectonic activity while you're building up this soil profile? You see what I'm saying?
Yeah, well, Steve just mentioned the runoff that almost certainly had to accompany the appearance of the dry land. So it appears that these sediments are typically at the top of the Precambrian sequence whenever they occur. And so I think there was all these igneous processes, metamorphic processes, accompanied with God's formation of the earth originally, and then the latest part of that was when God had the waters be gathered together into one place and the dry land to appear. There's almost certainly a lot of hydrological activity and sedimentation processes. In North America, it appears that these thick sediment sequences are along the western margin of North America in regions where there would have been runoff from the North American craton on the west, on that west coast. And so I have no trouble with these thick Precambrian sequences being associated with the runoff on day 3.
Okay, how much radioactive decay occurred during the flood year? That's again a continuing rate project question. But do you have any more?
Well, it seems to me if you take the radiometric, if you look at the amounts of uranium decay associated with the flood rocks, you have roughly 600 million years worth, 550 to 600 million years worth of accelerated nuclear decay during the flood.
That's a lot. Yeah, and that's what's interesting there is Dr. Snelling's his radiohalo research with the polonium, the different isotopes of polonium, some of them extremely short half-life, which must be continually resupplied by uranium, and then uranium decaying eventually into polonium and so forth. It has to be continually resupplied because the half-life of polonium is so short that it's not going to do much. It's not going to do anything really to damage the crystal structure That takes a lot. I think he said like 500 million, like 500 million atoms in order to cause
polonium atoms to produce a polonium halo.
Yeah, so that's a lot of a lot of uranium being produced very, very fast. So, did a lot of radioactive decay occur during the creation week, or as much of the presumed billions of years of pre-Cambrian radioactive decay? And this is an interesting question. An artifact of the originally created isotopic endowment in the creative rocks and in subsequent multiple resetting.
Okay, if we look at the radioisotope ages for Earth rocks, the oldest rock is dated at about 4.4 billion years. Mm-hmm. If we look at moon rocks and meteorites, we get a little extra nuclear decay recorded. The current estimate from meteorites is something like 4.56 billion years in these meteorites. So in my assessment, it appears that you had a great deal of accelerated nuclear decay. I would like to introduce another term. We talked about it during the RAID project: accelerated nuclear transmutation of elements during creation week. That it just whatever processes God used to bring the creation into existence, accompanying that was some nuclear transmutation. In other words, uranium being transmuted into lead. So it just at face value, it appears that something like 4 billion years worth of accelerated nuclear transmutation occurred during creation. So that roughly 90% of the total that we see recorded in these presumed oldest rocks occurred when God was bringing the earth into existence during creation week.
I have a question that was there any radioactive decay, since we call it decay, right, before the fall?
The answer, it has, I see no real alternative. It has to have occurred during creation week, before the fall.
So you're saying radioactive decay is not really a deleterious process, but it's something that is a necessary part of for creation to work.
Yeah, who was it yesterday attacking a Greek way of thinking? I guess it was Lady Faulkner. That's right. Yeah, as to what is good or very good. Is nuclear transmutation something that's not good? Is there any problem with having nuclear transmutation when God is forming the earth to be a very good place? I'm reluctant to say to claim that it's not, that there's I'm reluctant to claim there's a problem. It could be, as Danny Faulkner was pointing out, it could be some of these Greek influences on our thinking as to what perfect is. Like Plato's, ideal, this realm of ideals, that the perfect chair or the perfect whatever, that there is this realm of ideals where everything is the best it could be, and what we have in this realm are just approximations to these ideals, like the various chairs in the room are just approximations to the ideal chair in the realm of ideals. That this kind of Greek thinking may have influenced us, even as believers, into figuring out what very good must have been like in the original created earth.
Well, the very name radioactive decay, the decay part sounds bad.
Yes,
right.
Right.
Yeah, but just think for a moment. Would you like to take a book into into the middle of a nuclear reactor, sit down for 5 hours and read it? Radioactive decay is definitely deleterious to human tissue. So, although decay itself for the rock, it maybe is a necessary process. I don't think it's just that simple. It's
Yeah, yeah,
Yeah, but
and,
yeah.
and that's why I was
Yeah,
proposing this
transmutation.
alternate term of transmutation.
right.
And we grappled with this during the rate project, so because there were people on our team that had problems with nuclear decay before the fall, and so anyway, to me the case seems to be pretty strong that there had to be a lot of nuclear transmutation during Creation Week, and that this transmutation, there's a record of this transmutation in the rocks that are from that part of Earth history. They're there to, you have different amounts of radiogenic lead in different Precambrian rock formations. Right. That's an objective fact, and so if we're claiming that there was a lot of nuclear decay during the flood, we document that from our rate project through these polonium halos, through the helium, radiogenic helium and zircons. All these things are indicating to us that accelerated nuclear decay had to take place during the flood, but yet as we go further back in the rocks that have to be before the flood, before there are any fossils, we see increasing amounts of of these transmutation products, and so anyway, that's.
Do we see accelerated decay in those rocks in the earlier ones?
Yes.
Oh, we do.
Yeah, part of the zircons, for example.
Oh, that's right. They're 4.5 billion. That's right.
Yeah, they were 1.5 billion had a uranium lead age of 1.5 billion years. So that had to include all the nuclear decay during the flood, plus almost a billion years that occurred before the flood. Yes.
Going back to the craters in the Precambrian, and for us to say that that was part of the Creation Week, I still have a problem with it.
Okay.
And it just, the problem is, the sun, moon, and stars are created day 4, okay? And you've got the land emerging in day 3. So, seems like the bodies, asteroids, meteors, whatever, are gonna be created day 4, not gonna be created day 3. So that's a problem.
Yeah,
Okay?
it's a problem for most people.
Unless you're saying that they're hitting the earth prior to the creation of man. Okay, so I mean, if they're created on day 4, day 3's happened day 4, so it's sort of a very close event before animals on day 5 and 6. I mean, you've got a lot going on there, of course. But the other thing is, would it have anything to do with the flood itself? So we got just 8 people on the ark, and we've got, the fountains of the great deep breaking up. Could that be a cause of that? These actual some type of meteor hitting the earth as a form of judgment that would be indicated in the Precambrian rock. I'm just trying to.
Okay, well, we do see a burst of impacts during the flood. There are lots of impacts relative to the frequency after the flood. The number we observed today, the frequency that we've seen in human history since the flood, we have a huge number, a vastly increased number in flood sediments. The Chicxulub impact, for example, in Yucatan, is one example of a large impact during the flood, but there are dozens of good-sized impacts that took place during the flood. So something apparently disturbed the solar system that resulted in a very big uptick in impacts during the flood. But as far as these two Precambrian craters, those radioisotope methods are used to date those, and the radioisotope dates put them not in flood times, are not even close to being near the time when the flood began, but back, well back into the Precambrian time, which we interpret as when God was forming the earth. So that's an issue we need to deal with. I think it's not honest for us just to sweep it under the rug or deny it, but it's definitely something that needs to be explained.
Here's another one that needs to be explained. I'm going to have to move on.
I just want to say, John, one thing on that. We had there's 10,000 extinct volcanoes, right? And if these were going off at the time of the flood, and we see Mount St. Helens throwing boulders out of there 2-3 tons in size, and Mount St. Helens in the big scheme was nothing. What if you were launching huge rocks, mega size, and so then they come back, they don't reach escape velocity, they come back, and a lot of these craters are self-inflicted, and you could make a pretty big hole, or depression in soft sediment.
Yeah, but I say if you run the numbers, you're not going to get enough energy to produce these big craters like Sudbury or Verdifort.
Okay, we need to move on. And how was the heat generated by accelerated radioactive decay and catastrophic plate tectonics during the flood dissipated? I know this is an area of active research, so I guess we don't, unless Gene has, what's your favorite theory?
Well,
You have to be loud.
I like Russell Humphrey's rapid expansion space.
Okay,
And as you were pointing out yesterday, the neutrinos, if you switch from alpha decay to beta decay in some of these decays, neutrinos can carry out more energy. You still have kinetic energy electrons, so I don't think that would be as good as Russell's idea. It might help.
yeah, I wouldn't expect my idea to be a very good idea. I just have a master's degree in physics.
That was a good idea to investigate.
Okay,
And I'll put that back on my list.
wow.
I don't expect to do it.
Oh, I didn't expect it either. Can we fully determine the configuration of the pre-flood supercontinent Rodinia and then simulate the pre-Pangea plate movement early in the flood? That's what you were doing, right? That
Well,
kind of thing.
I showed today the kind of reconstruction, plate motion history. I believe we can be pretty confident about that as far as actually reproducing the mechanisms, the subduction history that causes that earlier breakup that I showed. I've made some progress on that over the last 5 years. So I think I'm optimistic that the answer to that is yes. Yes. I
Okay.
think.
Can we integrate into the simulation of catastrophic plate tectonics the multiple generations of large igneous provinces?
Okay, these are sometimes referred to as super plumes that arise and come up and produce these massive outpourings of basaltic lava. And I would say whether we can predict them, that they certainly are implicit, or I'm not sure we can model from scratch and explain why they are where they are, but for sure we get them in the kind of models that I've been working on.
Okay. Can we explain further the role of water in regional metamorphism and thus demonstrate that it can and did repeatedly occur during the flood year?
Well, this is detailed modeling, and I think, yes, I think we understand these things well enough to do that.
Okay. Can we explain further the repeated rapid formation of granites, even in the same region during the flood year?
Yes, you just need some rapid deformation to heat the rocks to melting point and produce the granite. So I think, in principle, the answer is yes. We just need more laborers. The laborers are few or even non-existent at this point.
Can we develop comprehensive models for the formation of the various types of ore deposits of the various biblical stages of Earth history, especially during the flood, that will also have predictive power to aid the search for and discovery of new ore deposits?
That's pretty ambitious. I think we can, in principle, say what's needed to produce the ore deposit. You need a source of hot rock. You need some melting that produces hydrothermal circulation and extracts these different metal ions from the in most cases surrounding sediments and leads to concentration into an ore deposit. I think there's fairly good understanding of how these ore deposits are formed, and you just need to he's asking for predicting how these circumstances arise in a flood scenario. But again, we're talking about a level of detail modeling that I think is pretty far away, and would require a lot of effort by some very well-trained and talented people. So I'm not optimistic that we can get a flood model to that.
And also to be able to use it to search for and discover new ore deposits. I think that Andrew had talked about using even the radio halos, because the uranium has to be carried, and they're also carried down cracks. The uranium has to be carried into that location. And so if we could trace back the crack from the polonium radio halo location, we would see where the uranium came from. But I don't know how accurate that is. Where do the craters on the moon, early and late more craters, and heavy bombardments, Venus, Mercury, and Mars fit in the biblical chronology of universe history? We'll just leave that for Danny, I think. How do we reconcile the radioisotopic dating of lunar rocks and meteorites, lunar, Martian, and asteroidal, with the biblical chronology of universe history?
Well, that gets
pretty hairy, I think.
Yeah, that gets back. I had some slides where I show some of the most primitive material that we have for our solar system, namely chondritic meteorites composed of chondrules, little spherical blobs of molten silicate that crystallize into the kinds of silicate minerals we see here on Earth. Most of the meteorites, or majority of the meteorites, are composed of these chondrules. So at some stage, the solar system must have been filled with molten droplets of silicate. Now, how in the world you get enough dust around for it to melt and form a droplet of silicate, a millimeter or so, or a few millimeters in diameter? That's speaking of a scenario that's much different from the typical nebular hypothesis that is currently the default model for the formation of our solar system. I personally am advocating that we have some creationists work on the processes that God used to form the solar system, which would account for, which would explain the origin of these chondrites, and also the fact that the chemical composition down to the distribution of the different isotopes for each element seems to be the same in chondrites. What's in chondrites is the same as what we see in the Earth, same as in the moon, same as what we see in the corona of the sun. Same elements. it looks like all the solar system was made out of the same recipe of elements. And so if so, how does that fit in with the Genesis 1 account of the creation of the earth and the moon and presumably the planets and other bodies in the solar system? That's a big area for research.
That's a Danny question. Where does the Noachian, Noachian or Noachian era in Mars geology fit in and correlate with the biblical chronology on the Earth? They're saying that there's evidence for a flood on Mars.
Yeah, it's interesting that the actual history of Mars, the different ages in Mars, one of them is the Noachian. Actually, the Noachian. That's the name they've assigned, and it's a time of water covering most of Mars, and an evidence of lots of drainage and erosion and water formed features. And so it appears that early in Mars history, it had a lot of water on it. And so again, that's a good question. It would appear to me the simplest explanation is that Mars, as God originally created it during creation week, had lots of water.
Are they getting radiometric dates from the rovers and stuff when we send to Mars?
No, we have no way. None of the rovers have had any ability to do radioisotope dating. The way some of these dates are obtained, though, is from rocks that are interpreted to be pieces of Mars that were blown off by meteorite impact on Mars. No, but presumably a surface layer.
Okay, this is it's 10 of 5. So we have I think 2 more. Is this 2 more?
Yeah.
I think okay. So this is finally into what things are we completely uncertain about. That is, we don't have a clue. We don't have questions and no answers yet. I would call these creationist frontiers. How was the fine scale layering in the fossil record produced? That, e.g., why is there only one species of foraminifera in one fine sediment bed, and then another species of foraminifera and another fine sediment bed above? So these are issues of paleontology, I would say.
Now, I talked about this fine layering in my talk.
That's right, you did. Mm-hmm. You want to say something about it?
Well, this paleontological dimension here that he's talking about, I don't have a good answer. I'll just say that maybe there's a lot of mixture of water bodies, and each one might have had its own foram population, and it depended on where that pulse of water came from that deposited that thin layer.
So your model explains the fine scale layering, but we need the paleontologists to explain this phenomenon of the different foraminifera in one sediment bed vis-a-vis another. Okay, let's get the last one. Where were all the land creatures, or how were they able to survive when the basal Salk megasequence was deposited on the this is the lowest of the megasequences. The basal Salk sequence was deposited on the globally extensive erosion surface. That's the great unconformity, produced by the rising floodwaters destroying the pre-flood world.
Well, on the slides that I just showed, that original unconformity at the base of the Salk megasequence did not intrude the entire continent. It was only the fringes of the continent. If you look at the distribution of the Salk sequence on North America, that's what you see. It's like an apron around the continent. It doesn't intrude to the interior. So the higher elevation interior was not affected, and the animals in that region survived that destruction of the great unconformity.
So I guess the apparently the paleontology in mid-continent, that's what he's talking about, is different. Well,
So I'm saying that this is one that could be moved up on the list. Some of the ones in the preceding list I consider we really don't have a clue about, a good answer for.
okay.
So I would move that one up to a little higher, in a higher category.
Okay, so we have what we've seen from the conference is just like John's comment. Then some things maybe should be moved up, others should be moved down, and this is the beginning of a very important dialogue to assess as a creationist as a whole where we need to be concentrating our research, and so we can significantly advance our cause. And also, I think, significantly advance the understanding of the Scriptures and to the glory of God. Well, let's close this conference in a word of prayer. Father, we thank you for these 3 days we've had, one night and 2 very full days. We thank you for all of the experts who have contributed. Some of them who already have left. Danny and Rob Carter and Todd, who had to, again, could only attend by Skype. We thank you, Lord, for the contributions. We thank you, Lord, for giving each of us the opportunities to study in our fields so that we can contribute and explain things. Help us, Lord, when we explain things to be clear to those who don't have the understanding, the expertise that you have allowed us to have the opportunity to acquire. And we pray, Lord, that through all of this, you will receive the honor and glory. May we be a blessing to you, a blessing to one another. May our attitudes toward one another be ironic. We are brothers and sisters in Christ, and we work together to find the solutions to these to admittedly difficult questions. And may Lord again take us all to our homes safely. And we pray, Lord, as this conference has kicked off this year, and we look forward to again for next year, give us a productive year of research in the areas in which we've identified where we need to be focusing. Again, we thank you for this opportunity, for your love, for your grace towards us. We pray all these things in Christ's name. Amen.
Amen.
Okay.